this recording, and we are good to go. All right, so let's redraw this control volume a little bit bigger. So we'll have state 1 and state 2 at each end. And so we have then in the reservoir, we'll call that P1. So we have P1, V1 equals 0, recall. We have T1. And out here, we are going to have a velocity, right? The environment far away from the tip of the nozzle is going to be quiescent, but we should have some sort of velocity at point 2. We should certainly have a velocity. That's what we're trying to solve for here. So we have P2, T2. We do have a V2. Again, we'll do aggregate velocities. And that looks pretty appropriate for applying our law that we found. Here was going to be that the mass flow rate times the change in enthalpy plus the change in velocity. So basically, the change from potential energy inside here, we have no velocity. We have a bunch of potential energy stored because we have a pressurized system. Is going to be converted into a velocity change and a relative change in enthalpy, right? That's what we're looking at. So for state 1, we have delta MH, M1, H1. For state 2, we have M2, H2. For velocity, we have, for the first state, we don't have any velocity, right? We have velocity is 0, and then we accelerate through this system. So for state 2, we have plus M2 V2 squared over 2. All right, so this is going to be equal. All right, so let's apply continuity here, because we see we have M1 and M2. If we apply the continuity equation here, the macroscopic version is going to tell us that delta rho VA equals a change in the mass flow rate with respect to time. All right, we know we're operating at steady state, so we won't have this change with time. And so all we can really say is, without that change in time, that M1 does equal M2, but what we can say is rho 1, A1 equals rho 2, V2, A2, but this is also equal to M dot. Right, this is M dot 1 and M dot 2, so we don't need to worry about this, and furthermore, we can drop it from this equation, right? We have M dot multiplying everything here. So, boom, boom, boom. All right, so we have H1 equals to H2 plus that exit velocity that we were kind of seeking. So if we can get a handle of the change in enthalpy of this system, then we should be able to get a handle of what this exit velocity is. In fact,